Thanks for coming, everybody. My name's Fritz Klassner. For those of you that don't know me, I'm the Natural Resource Program Manager with Office of Maunakea Management. Rose has recently done the oral defense of her thesis and is all but done in turning in the written copy to the university. So she graciously, we waited until her oral defense was passed, and we thought we would mostly be done with the written part. But so anyway, fortunately for all of us, Rose is going to be sticking around after graduating here. She's going to be helping Dr. Perroy working with the spatial data lab at Hilo, the SDAV lab, helping most immediately, as she said, with some of the eruption monitoring work. They have thermal cameras and drones and do a lot of the thermal mapping that you see on the USGS and civil defense. That's a lot of that work is done by Dr. Perroy and the other folks in his lab, including Rose. She'll also be working on some additional sea level rise work, including ancholine ponds and a nature conservancy project. When I hear ancholine ponds in the coast, I think of Kapoho. I'm assuming it's in the vicinity of that, somewhere in that part of the island, maybe.
Yeah.
She can explain. But otherwise, Rose Hart is a all but finished master's degree student here at Hilo in the TCBS, the Tropical Conservation Biology and Environmental Studies program. She's getting her master's thesis on sea level rise using 3 sites here on the island of Hawaii. She's going to talk more about the methods and techniques that she used, and as just sort of alluded to, there's a lot of applicability to other aspects of sea level rise, but also other concerns, whether it's how to use drones or unmanned aerial systems, volcanic monitoring, erosion monitoring. So there's a lot of applicability. It's some really fascinating technology. Rose originally came to Hilo. Well, I'm not sure where you got your undergraduate, but
yeah.
You got it here?
Yeah.
Okay, she got her undergraduate here at Hilo. She's originally from Southern California, but we are very glad she's here and very glad that she looks like she's going to be sticking around for a while to help. And with that, thank you, Rose. The floor is yours.
Awesome. Thank you for the introduction. Oh, thank you. All right. Well, as Fritz had introduced me, my name is Rose Hart. I'm a graduate student here at Hilo. I am going to graduate on Saturday, and I will submit my thesis any day now. But tonight I'm going to talk to you about my research focusing on shoreline change at 3 unique coastlines on Hawaii, and how we went ahead and did that mapping and how it relates to coastal zone management here. So I'd like to give a brief overview. I'm going to give an introduction on coastal vulnerabilities in general. Then we're going to highlight coastal vulnerabilities in Hawaii. And then I'm going to talk about some statewide adaptation strategies that are going on here. And then address some knowledge gaps for Hawaiʻi Island specifically. And then we'll go through site by site and talk about methods, results, and some conclusions and final thoughts. Yeah, we'll have some final thoughts, and then I'd like to open the floor for some questions and discussion. So I'll go ahead and get into it. Can everybody hear me okay? All right, if you feel like you need to move up, that's okay. So just to start out, coastlines are very important for a variety of reasons. First and foremost, perhaps, is trade and transport. We need them in Hawaii, for example, to get some goods over here. They have a lot of ecological importance as well. Another example here in Hawaii is the monk seal. They depend on the coast for breeding and rearing their young. Also subsistence. People go to the coast to fish, and fish ponds are one example of that, how traditionally people here have used the coast to gather food for their communities. And also tourism. So this is a basilica in Italy. It doesn't look coastal from this picture, but it is coastal. But we like to go to these places that have rich cultural history, and oftentimes these are also places that are built along the coast. And lastly, is coasts offer a strong sense of place, and you all, I'm assuming, live here in Hawaii, and I'm sure you feel that living here. There's something about being at the interface of the land and sea that just makes you feel good in a way that you don't get in some other places. It's just special. And so a lot of other people think that coasts are important and valuable, And in fact, we can expect in about 40-something years, 42 years, more than 1 billion people will be living in low elevation coastal zones. 1 billion people. And this is a bit concerning. And I probably don't have to explain this too much, but it's concerning because of sea level rise. And so what we're seeing here is different scenarios of possible sea level rise by the year 2100. Our if I can get the laser, our x-axis here is time, and our y-axis here is global mean sea level in meters. And basically what we can see is that by the year 2100, we're almost guaranteed 1 foot of sea level rise. Pretty much without a question, that's what we can expect across the globe. And it's also very possible that we could experience 3 feet of sea level rise. And that really scares me, especially living on an island. So we want to understand this problem. And when we think about all of these things that draw us to the coast, and we think about sea level rise and coastal vulnerabilities, you know, we start to see how these systems change. Our monk seal here is on a very small and increasingly declining beach that's been developed in Honolulu. We see king tides affect these areas that we previously depend on. And we see places that we want to go visit become flooded. And areas that are at the interface of land and sea become destroyed due to these natural processes that are only being intensified as the climate has been changing. And so what's really important is to have science-based management strategies. And so this is a field that is being explored today. And so scientists are starting to work with different types of managers, engineers, educators, scientists, and to try to produce policies that can better protect our coastal systems from hazardous development, but also protect people who live along the coast from hazardous coastal processes. And so this is where we are. We are here, in case anybody forgot, we are surrounded by ocean. And with that, we have several challenges that we are faced with. So we have problems with coastal erosion in Maui and Kauai, and we see communities be undercut that are very popular places for people to go to. We see that we're losing our beaches in Waikiki due to the way that we have engineered them and the way that we've developed the coast. We're not allowing this beach to move the way that it might. And we're also doing large-scale nourishment projects to continue to have this beach. And so these problems are very well understood in Hawaii. The Coastal Geology Group over at UH Manoa has been doing a lot of really incredible work to map and monitor coastal erosion and sea level rise. And what has come out of this research group is that they've quantified more than 21 kilometers of coastline have completely disappeared, or 21 kilometers of beach coastline have completely disappeared due to erosion. And these losses get exacerbated by things like sea level rise. And using this data, coastal managers in Maui, for example, have taken this information of shoreline change rates and applied it into adaptive planning policies. So a shoreline setback, for example, where you can develop relative to the shoreline. And so what they have said is that we're going to take our erosion rate in feet per year, multiply it by the life expectancy of a building, which is generally 50 to 100 years. And then we're going to take that product and add it to the original shoreline setback designation. So for Maui, for example, they say that your shoreline setback will be 25 feet from wherever your designated shoreline is. And so in doing so, you're producing a scientifically based buffer from where people can and can't develop based on the existing hazards of that place. And so this is really great, but there's been no analyses done for Hawaiʻi Island. And this really caught my attention because we have 430 kilometers of very diverse coast, and at the county level, our shoreline setback is 20 to 40 feet. It's a minimum of 40 feet for all lots, with some exceptions that allow for 20-foot setbacks. And well, this is problematic and catches my attention because there's no research supporting that that setback is appropriate for such a diverse coastline. And we're already seeing some of the problems from, you know, such a policy in developments today. We're already being impacted by these changes. So that leads me to my project objectives, which first were to quantify past and present shoreline change rates using existing data sets like historic aerial imagery, but also using new data sets like the drones or small unmanned aerial systems, sUAS. You'll see that acronym a lot in here. And then we wanted to estimate future impacts or vulnerabilities to my different study sites using sea level rise data and other geospatial data. And then lastly, we wanted to produce results that could really inform local coastal zone management strategies. So how can our science become actionable and inform and improve our community? So I'll introduce my study sites now. So Hāpuna Beach is located on the northwest of Hawaiʻi Island, and a lot of the other studies that I briefly highlighted focused on beaches. So this is more relevant to some of the previous study sites. And by this point, you might be thinking, like Fritz had said earlier, we're here for an Office of Mauna Kea Management talk. We're thinking about the mountain, but I promise you, Hāpuna is right there. It is in an area where there has been a Mauna Kea flow, so it's related. My next study site is the Honoli'i Sea Cliff, and in particular, I'm interested in this region of the cliff. And actually, I was just given a paper today that talks about that same cliff and discusses some of the research that I've done. And so we're interested in this site because there's a couple that still live here, and their house is becoming destroyed due to the undercutting of this cliff, and that's really concerning, and this isn't the only example of this. And also, this is part of Mauna Kea, so it's still related. And then there's Kapoho Tide Pools, and this area is interesting because it's subsiding. So it's sinking due to the volcanic activity, and I imagine I will have some additional work to do after this lava flow to look at how this area may have changed. But it's actively subsiding, and so that will exacerbate the effects of sea level rise. So as the tide comes up and the land is slowly sinking over time, your water level gets higher and higher. And this site doesn't have anything to do with Mauna Kea, but it's interesting nonetheless, and we're going to talk about it, and it's going to be a great story. But anyways, moving on, I want to talk more about Hāpuna Beach for starters and some of our methods here. So we conducted 7 small unmanned aerial system surveys, drones, just to remind you all. And so we scattered these out. We try to do it every other month between January of 2017 and January of 2018. And so before we were able to fly our drone, we needed to get coordinates of ground control points. And so that allows us to make a super accurate map that can allow us to do further analyses of shoreline change or sand transport, for example. So we had a series of invariant features. So these are permanent features, and a series of variant features. So these were often markers that we had put out on the sand, and these are moving, and these points allow us to see change over time. And so we surveyed these with a total station. And so we repeated this every time we went to Hāpuna Beach. And then we were able to fly our drone. And this is what a flight path looks like. And if it's hard to tell, it's a parallel survey to the shore. And when we do this, we take a whole bunch of pictures that have a variety of overlap, and we create something called an orthophoto mosaic. It's just like a mosaic. It produces one big picture out of hundreds of pictures. And so we can process these data into a software called Pix4D, but it allows us to produce different products. And so we can produce a super accurate data set, basically accurate to 3 centimeters. And that's pretty incredible. And so, like I said, we get 2 products, one being the orthophoto mosaic. And so just to show you that, it's one big picture out of all of the pictures we take with our drone. And then we can measure different uncertainties with our shoreline from this data set. So we can measure a shoreline, which we identify as a beach toe or the low water mark. And there's different uncertainties. We're not going to get into it, but I just want to let you know we address it. And so we do that for each time we surveyed. We have 7 shorelines and an estimate of their uncertainties. And then we get this densified point cloud. And what that looks like is just a bunch of points. So it turns all of these pictures that we take into a bunch of points. And what's really cool about this is that you can process it very similar to LiDAR. And what that just means is you can get different levels of elevation all the way down to the bare earth. And so that's really important when you're wanting to do different types of geospatial analyses that are super accurate. So for example, we can take these point clouds and process it like LiDAR into a digital elevation model. And so what this is showing is from one of our surveys, the elevation, the blue colors being low elevation, 0 meters, and the warmer red colors being higher elevations, so as high as 35 meters because there's trees and pavilions over there. So that's what we're seeing. But some problems with this is that it's a little bit noisy. So if you can see, there's kind of these spots up here. Does anybody want to take a guess what these are? Any guesses? What could these dots be? They're umbrellas! And so we don't really like that because when we're trying to measure change of the beach, we want to get information that's just the beach. We don't want any other umbrellas or lawn chairs. That doesn't mean anything to us. So what we do is we do some processing. So over here, these are those umbrellas, and we take them out. So this is what it looks like now. And that's pretty great. And so we do some additional validation to see how accurate these elevation models are so that we know, okay, this is the information we're saying. How good is it? What is it telling us? So we find out that our elevations are accurate to 5 centimeters. So that's also pretty good. We're happy with this. And so I have a field crew who goes out and helps me do this. They're great. They're mapping the lava flow right now. So now we've produced all of these DEMs. We have all of our short-term shoreline data that we've collected with the drone. And so now we want to compute long-term shoreline change. And so this is just an example of some of the data sets that we used, but we went and gathered as many old historic aerial photographs as we could get. And we georeferenced them. So basically tied them to like an actual map so that they were fit into like where they are in the world. And so then we also identified different uncertainties for these. We're not going to go into it, but just want to acknowledge it. And so we had a total of 7 different historic shorelines that we were able to produce in this process, and then including these short-term shoreline change data sets, we were able to include the more contemporary shorelines for analyses. And so we can use a program called DSAS, Digital Shoreline Analysis System, and so it allows you to compute rates of change, specifically for shoreline data. And so let's look at some results. Talked a lot about methods. So what we've seen with the short-term shoreline data is that Hāpuna Beach is very dynamic. So the shoreline does this dance throughout the year where it moves about 7.3 meters. And so that's a lot. That's like 23 feet, something like that. And so it's moving a lot throughout the year. And when we look at the intra-annual change, looking at these digital elevation models, we're able to see where sand is building and where sand is being taken away through time. And we're able to validate some of the changes we see with imagery. And if you've been to Hāpuna, you might recognize this rock outcrop on the beach. This rock outcrop is a really great validation source for us because we can look at sand get piled up on it and get scraped away from it. And so we see it get exposed and buried. And we can look at these digital elevation models we produce where we say these green areas are where sand has built up, it has accrued. And we can see these purple areas where the sand has eroded and been washed away. And again, we can see these changes are real with the imagery. And so this is just to show some of the changes we've seen. So I'll go back. This is between January and March, March and May of 2017, May and July, July and September, September through December and December through January. So you see there's a lot of things happening here, and there's something kind of crazy happening over here in September, and we have some ideas of what that could be. But the main point of this story is that we see the species changing a lot, and we're able to quantify it and map it with these drones on a scale that hasn't been done before. So it's really exciting to apply this technology for this kind of application. And so now looking at long-term change, what has Hāpuna Beach been doing over time? We're not going to look at all of the imagery data sets, but I'm going to show you a little bit of them. But this is from 1975, 1964, we're jumping back in time, 1988, 2000, and then 2017. And so it's kind of hard to tell, I know, because of the blue and the white background. But what the story is that the shoreline has been going back, and in some cases it goes up a little bit. And so these are all of the errors we had used to compute different shoreline changes in the long term. And then when we look at all of the shorelines over time and we want to compute change here, so these are the results now for long-term shoreline change, we see that Hāpuna Beach has been eroding at a rate of 18 centimeters per year, plus or minus 17 centimeters. So what that means, we're trying to figure out. But this has been change that we've measured since 1964 up until today. And why we think that the erosion is the way that it is with an uncertainty that's the same as almost the erosion rate is because when we look at all the shorelines, they're all over the place. And we had measured in the short term that Hāpuna Beach varies by 7.3 meters. And so what we're suspecting is that this beach is just moving, going through different oscillation cycles of maybe periods of erosion, maybe periods of accrual, but it's variable. And so maybe it might not be eroding at a rate that is quite as significant as our other island neighbors where they're seeing more destructive erosion. We're just maybe not quite there yet. And then when we look at sea level rise and possible impacts due to sea level rise, we wanted to look at maybe the smallest beach. So we recorded our smallest beach area to be in March and our largest beach to be in July to look at the seasonal morphology of the beach and how it would be affected under different sea level rise scenarios. And so this light blue is our regular high tide mark. And then this medium blue, this is our 1 foot of sea level rise. So you can see it better here in the larger beach, 1 foot of sea level rise. And then our darker blue is our 3 feet of sea level rise. And so what we see is under 3 feet of sea level rise, if the beach remains the way that it is, then it will be completely submerged. And it won't matter what the seasonal effect of the beach is, it will just be covered. But, you know, we should keep in mind that if we don't engineer the beach and let it, you know, migrate the way that beaches do, we won't have to worry about problems of losing it altogether. So it's important to keep that in mind. Beaches are dynamic systems in and of themselves, and the way that we build around them can affect whether or not we lose them. So some final thoughts here are that the sUAS, the drones, they're very effective tools for mapping beach morphology changes and shoreline changes over time. We also see that the beach is very dynamic and that through this dynamic state of the beach, we're also able to observe some long-term erosion. And with this information in mind, we would recommend that Hawaiʻi County considers this kind of application for other white sandy beaches in Hawaii, and considering what islands like Maui have done and taken these erosion rates and plugging them into a more science-based shoreline setback. If they can do it, why can't we do it if we have the data? So moving on, we're going to talk about Honoli'i. So we followed the same methodological approach. We took a whole bunch of pictures throughout the year. This one has a lot more pictures because Honoli'i is so close that we could go every month or as much as possible. So Here we produced some orthophoto mosaics, and then we also included extra oblique images. So we took images at an angle. And this is really important because we can get better data about the cliff face and perhaps areas that are being undercut. And this is important for this study site, again, because there is this property here obviously being destroyed. So what some of these images look like are like this. So these are the point clouds. And it's pretty incredible what we're able to see with these. And this is all the debris that has piled up at the base of the cliff over time. And so using these data sets, we're able to identify where the cliff is. We're able to identify where it is better based on where it's undercut. We don't want to include areas that mark our cliff shoreline that are actually a part of the property itself, right? Because it's just undercut. So we identify the shoreline for the cliff because we want to look at change of the cliff over time. So we do that for all the contemporary shorelines. And then we do the same thing for our historic shoreline data sets. So we had quite a bit fewer for Honoli'i than we did for Hāpuna. But we were able to get back from 1964 up until 1987. And actually we have one for 2000, I think that's included. But we also identified the different uncertainties associated with these shorelines. And so here is the short-term shoreline change. And it might be hard to see, but the story here is that the shoreline has been retreating. So here, this is our first shoreline, this dark red, and then this brighter pink. This is the more recent shoreline. And so you see it's gone back quite a bit just in a year alone. And so we're able to measure that. And so we found that there was a maximum retreat in just a year of 2.4 meters. And that's a lot. That's not insignificant. And so with this in mind, you know, we get a better idea of the change that's happening here. And so, for example, we can identify episodic events. We know that this is retreating, but is it retreating uniformly? And the answer is no. So this is October 2017, or this is June 2017. This is wrong. This is June 2017, and this is October. And so what we see is this area is going back. And so under here is some cliff that has also been deposited. And so it's pretty incredible. We're able to identify, because we're able to survey so much, we can identify these short-term episodic events. And so we found that there was a total loss. We're estimating a little bit over a cubic meter, but we think that this is an underestimate because we still need to measure the amount deposited at the base of the cliff. So this is just an early kind of proof of concept. We can use these data sets to quantify how much sediment exactly is falling off. And then when we want to understand our long-term change, how much has it eroded since the 1960s? And that rate comes out to be 13 centimeters per year. Yeah, so that's 13 centimeters per year. And actually between 1964 and 2018, it's eroded about 6 meters in one zone. And there's some larger uncertainties there because with the historic imagery, you can't see the house as well, and you can't see the cliff features as well because the pixels are larger. But that was our estimate. And so some thoughts here is that the erosion at this cliff is very serious. There's a couple who lives in here, and they're staying there, and they could go down with this house. And that's horrifying. And there's been plenty of cases of other houses that have this issue along the Hamakua coast, and they're just not getting the care that they need. But if we're able to do surveys here, and at sites similar to this at a greater temporal scale, we can better inform these communities. We can better inform these homeowners of the hazards associated with where they are. And we can prevent development on cliffs that are zoned for housing. So we're able to do a lot. And so we'd suggest that the Hawaiʻi County takes these methods and these data into account and consider making cliff setbacks based on erosion rates, specifically episodic erosion rates, because that often doesn't get described in your long-term rate. So moving on to Kapoho, this is a little bit further south than Honoli'i, on the east side, and so we follow the same approach to collect our drone imagery. And so we did a series of total station work to gather our ground control points, and then we flew. This is David Russell. He is one of my interns last summer, a PIPES intern. And so we produced 2 orthophoto mosaics. We did one during low tide because we were really interested in anchuline ponds, and we'll highlight those in a little bit. But we were really interested in the anchuline ponds and the flooding here, and how flooding might be exacerbated during higher tides. So we went during a low tide, and then we went during a king tide. And we were actually able to go survey as the king tide was coming up at its peak. So our data was real-time data as this event was happening, which is pretty remarkable to me. And so with these data sets, we were able to compare where anchuline ponds and where high tide marks were before king tide flooding and then during the king tide. And so what we can see is the blue is our water. And so here is our October 2017 low tide survey. The right is our June 2017 king tide survey. And so what we see when we compare the two is that the anchuline ponds ended up resulting in a lot more inland flooding. And so this is where people are trying to drive to get into their homes. We also see that there was a lot more inland flooding, and in fact we measured it to be 60 meters greater than the mean higher high water mark in some places. And with this in mind, these are examples of what it looks like on the ground when you're there. This is actually during regular high tide. This wasn't during the king tide. This just shocked me. But this is during the king tide. And when you look up a little closer, you can see these ripples on this new road that was built. And what we saw was that 97 out of 143 parcels were affected by the king tide flooding. And so again, this just reiterates that, and you see this line here is highlighting our mean higher high water mark, and so you can see how much higher the king tide flooding was. But we were also interested in perhaps the cesspools or on-site waste disposal systems more properly, because some places have septic tanks. But we wanted to see where these were and which ones might be affected, because if you guys don't know this, out here is the Waialapai Marine Life Conservation District, and there's a lot of really important coral species out here that don't like on-site waste disposal systems because they release a lot of nitrogen into the water. 27% of nitrogen inputs in this area are from the on-site waste disposal systems. And so that's just bad news. People swim in there. You don't want to swim in the water when you know that there is, human waste products in there. But we're able to see and estimate that maybe 39, this is probably an underestimate, 39 on-site waste disposal systems were affected during this event. And so now projecting into the future and looking at how sea level rise might affect this place, we see that by 2028, so 10 years from now, we could expect quite a bit more flooding. Let's just take a look back today, 10 years from now. Oh my gosh, this is 2043, 25 years from now. Oh my gosh, 2068, 50 years. And now we're at the end of the century, nearly. And these time intervals might seem a little strange, but they were chosen collaboratively with the county based on knowledge of the life expectancy of certain buildings down there. So we chose the present day to the end of the century. But what we can see here now when we think about cesspools is that about 88 cesspools we could expect to be affected here. And that's pretty much all of them in this study site. And one thing to note is that we haven't gone out to survey in where exactly all of these are. This is just a county provided spatial data set. So we haven't gone out to validate if there's some that haven't been recorded that perhaps were abandoned when a house was taken down or not. or if any have been upgraded. But regardless, this is shocking, and it's something that we should be concerned about. And so what we can say here for sure is that nuisance flooding is already a threat. So things like the king tides that are already happening, that's a serious threat to this place. We're already experiencing these impacts. And as sea level rise and subsidence continues here, which it will, there's going to be some serious problems, both structurally for developments, but also probably ecologically for the reef that's out there. And so it's scary to think about going into the future. But with this information in mind and what we're able to do with these data sets is inform the county and maybe suggest that we should have perhaps an elevation-based setback. Maybe having a horizontal distance from your shoreline isn't going to cut it because this area is low elevation and we know that it's going to continue to sink. And like also, who knows now what's going to happen with these earthquakes and subsidence that's happening on the other side over in this region. So we need to be aware of the technology available and how we can harness it to better protect these people down here and also our coastal resources. I don't really want to end on like a doom and gloom. So we're going to go over the project objectives and talk about what we've accomplished. So first, quantify past and present coastal changes. We were able to do that. For Kapoho, on the other hand, I do want to point out that we focused mostly on the present day vulnerabilities and future vulnerabilities. And then we wanted to estimate future impacts by merging data with sea level rise projections and other geospatial data. And then lastly, produce products that can inform local coastal zone management strategies. That was really the goal. And I've been working with the county pretty closely, and Bethany Morrison is a planner down there who is on my committee. They're very interested in moving forward and doing more surveys to better improve our methodologies, but really try to adopt them into their planning strategies. And so some overall conclusions is that, first of all, failing to adapt is not going to be an option for these coastal communities. These hazards due to sea level rise or erosion or subsidence are going to persist. And these are challenges that we have to face head on. But with that in mind, it's not impossible. We have really incredible tools. We have really incredible scientists who can creatively problem solve and strategize how we can build adaptive coastal communities. And with that in mind, I think with a lot of engagement, this is just an example of some of the people I've been working with, but through creative and collaborative engagement with different agencies, both private or state agencies, for example, you can accomplish really great things. And I just want to offer an example of that. So myself, my advisor, Dr. Ryan Peroy, and Bethany Morrison, who I had mentioned earlier, have been working closely on the sea level rise risk assessment through Nature Conservancy and NOAA. And what this project is doing is mapping sea level rise. This particular one is focused on the Kona coast, but mapping sea level rise and its potential effects on ancholine ponds. And so this is an example of this product, and you can actually go check it out and play with it. It's live now. And you can see where we might expect ancholine ponds to be impacted, where new ancholine ponds might pop up, and what that might mean for transport of certain invasive species. But it's important to keep in mind because people want to develop in these areas, but if we can know and predict how these areas might change in the future, we can avoid some problems. And so this is also really exciting because we're expanding over to Kapoho, and we actually just put tide gauges out there, or tide loggers out there a couple months ago, and we're going to go retrieve them, mostly out of fear of the lava flow. But we're going to go retrieve them and see what we get with that data. But we're starting to expand to other parts of the island to understand vulnerabilities to other coastlines, particularly where there are ancholine ponds. And so it's a really positive step in the right direction for coastal zone management here. And I think that there's going to be a lot more efforts coming up as we keep the conversation about Hawaiʻi Island specifically going. And so with that, I just like to say thank you. It was a lot of talking, a lot of information. But I really appreciate you taking your time on your Thursday night to listen to me. And if you have any questions, I'd like to open the floor to that. Or if you have some discussion topics, I'm open to that too. And just really excited to talk story. So thank you. Yeah.
Is anybody looking at this as far as Hilo Bay is concerned?
So yes, there has been some work done on Hilo Bay, particularly because of the history of tsunamis. And so the NOAA Digital Coast program has mapped different levels of sea level rise for Hilo Bay. And the different scenarios aren't quite dynamic in terms of like if a tsunami came again and what that would look like. But what they do have is different like 1 foot, 3 foot kind of scenarios, and then different extremes of greenhouse gas emissions and how that might exacerbate sea level rise. And so you can kind of toggle with that a little bit and see how Hilo Bay might be impacted. Yeah.
You know, the Honoli'i case I think is really interesting because you have on the one hand a natural hazard, a house that never should have been built where it was probably, and yet you have people whose whole life savings has been sunk down on that piece of property.
Absolutely.
And to me, it represents a real challenge in terms of, you know, public safety and health and good government. Can you really just evict these people from an unsafe house? Can you condemn it and throw them out? I mean, what have you discussed this with county planners?
Yeah, that has been a major discussion topic for us. And so, yes, the county could condemn that property. And even at the county and state level, it could be bought out. But the problem is that there aren't funds to buy it out and to take care of that property. And so we're kind of in this limbo state where the only thing that can happen is that we can require these homeowners to continue remodeling. And so over the summer, the homeowners were required to do some remodeling that had to be completed by September of 2018. And so that is intended to be a mitigation effort to prevent future hazards here. And so currently that's the strategy. We don't really have an effective property buyout system, and that kind of requires some more capacity with insurance companies and their relationships with the state and the county. But it is an issue, and the only way that it's really being addressed and mitigated right now is by requiring them to do these remodelings.
Isn't that the house that they had put a veneer of concrete on
Yes.
the face of the cliff several years ago, and that's all gone now?
It's all gone, and so actually all of that debris at the base of the cliff is from that cement armoring.
Yep.
And what had happened was they had put up that coastal armoring, and there had been 2 really heavy rain events, and you know, the cliff was doing things and it caused cracks in the cement armoring, and so it all fell out, and when it fell out, it took a bunch of the cliff with it. And so there have been several instances of other properties along Hamakua that have requested to have cement armoring that have been completely denied because of this situation. It doesn't work here. So yeah, there was that, and that definitely kind of catalyzed, I think, a lot of the problems that we're seeing more frequently today.
Because there is the Wailuku River, the apartment building has armored their part of the wall, but that's the river.
Yeah, so we also don't have any riparian zone setbacks for how we develop or build along riverine systems. So that's like another major data gap and another big question about how we develop in these areas, because we don't have rules or regulations in place to manage those kinds of developments. So that's why those things happen over there. Other questions? Thoughts? Yeah.
2 thoughts, just as a note. I grew up in a house on Honoli'i, Poly number 2, and it had a line of hala trees in the front.
Yeah.
And I heard they're all gone now. In the Hamakukos, just sheds, you know, that's how it is.
Yeah.
I did want to ask about the Hāpuna Beach. Since the hotel went in, did you notice any difference in how the beach behaved?
The beach didn't change at all. Yeah, no, it hasn't changed at all. I think the more concerning aspect right now is that there's been more development down there, a little bit closer to the rocky part of the cliff line, and that might be a little bit more of a concern, but the beach has been fine. The vegetation line hasn't changed too much in the past. It just fluctuates a lot seasonally. Yeah.
I have a question, Rose. So if the stars could align and the county could figure out what setbacks value should be, how much work would it be to, you know, does the county have the data to say, here's where here's cliffs, here's beaches, I like that term, and here's, you know, subsidence areas, so that, you know, do they need to collect more data to even, if they were to implement some of these recommendations, that there's more just a basic data collection, and then how much effort would it be to actually go through and, assuming you knew what the setbacks wanted to be, to actually sort of draw the lines on the map so that then you could communicate that information? Is that an easy task or years of work?
No, it's not an easy task. We don't have a comprehensive map that describes the different types of coastline. So we have general information that says this is our special zone management area, this is the coastline, and we have that. We also have geological maps that will indicate areas of subsidence, but not like on the scale that you're talking about. So I think a starting point would be to produce a comprehensive map of the different coastal categories for Big Island. And then as far as determining appropriate setbacks, I think it would be a case-by-case basis. So how I would envision doing it is that if you have an area that is zoned for a certain type of development and it's in your special management area, it's within your shoreline setback zone, you could focus on that specific proposed development and say, hey, we're going to do this analysis with this historic data that we have, with LiDAR data that we have, with other data sets, and we're going to let you know how much this area has changed over time. And then we're going to tell you based on that what is reasonable for you to build based on the existing hazards here. And so I think it would be more like a place-by-place for any region that could be developed, or where people are trying to build a house on the coast or a hotel or whatever, and you'd have to do it that way, because for places that are already developed, it's not that informative. They're already there. But yeah, it would be time intensive. And then also just to get the approval of the shoreline setback rule amendment. And so that's kind of the phase that we're in right now, is to allow the county to have the power to enforce a science-based shoreline setback. And it doesn't have to be like strictly written in the rules and regulations, this much times 50 plus 40, you know, they can just say based on like a site survey or site analysis. And that can be written in the language of like the legal writing. Yeah.
Well, when it comes to building in coastal areas, I think that there has been kind of a loophole that favors property rights. Mm-hmm. So even if your setback area is, you know, by all, it should be 40 feet. If that doesn't give you enough buildable space for a house, then you can encroach into the setback area,
yes,
a certain distance.
Yes.
And that seems to me to encourage development where perhaps none should exist.
Mm-hmm. No, absolutely. And I think that's a great point. And I think that that's where enforcing these longer term analyses, like going back in historic data sets and seeing, we've seen this much change. And so based on this knowledge, we're going to say, maybe you don't develop here. Or we're going to say, you have this much space. Do you want to develop here, or do you want to look at your other options? Because
Do you want to build a tiny house?
Yeah, totally. It's the in thing right now. You'd think they would. But yeah, that is a loophole that we have right now, where if you have a lot that is maybe only 50 feet long, that lot doesn't really exist, but just hypothetically, if you have a lot that's long and your minimum shoreline setback is 40 feet, they'll let you build earlier, just for those of you who don't understand that. And that is a problem that we have here. But including the science, I think, could better inform that and better prevent loopholes like that. Yeah.
Almost sounds like the homeowner should do a shoreline assessment or a setback assessment, kind of like an environmental assessment, because it's so individual.
Yeah, so that is a requirement. So for properties that are going to build and they're within the considered special management area, they do have to go through a permitting process to get approval, and a site surveyor or a site inspector will go and tell them where their designated shoreline is. But shoreline surveyors are few and far between, and sometimes there's other interests that get in the way, and so these inspections might not be as thorough as we'd like them to be, and the enforcement isn't as present as we'd like it to be, and so that's another challenge that we have. But there is a permitting process.
Will any of this work? I mean, we have lava hazard zone maps on the island, and people build.
Yeah, no, that's an excellent point that you bring up, and something that has been a discussion currently. Like, why do we zone these places for development when we know the hazards that are associated there? And so there's some political boundaries there that, you know, the public doesn't get very involved with, but there's some other interests there that allow these things to happen. And I don't really know how to get around that, but for places, you know, built along the coastline, for example, we've seen it work for Maui. And if they can do it in some of these places, we can do it too. They also have cliff-based setbacks that are just based on lot depth. And so if you have a sea cliff, then based on your lot depth is how close you can develop to the cliff. But there's examples of this working, and for places like the lava, that's not really my expertise in the zoning in that area. But we do need to think more critically about where we're allowing development and what we're zoning and where we're zoning it, so that we're not putting people in danger and not putting resources in hazards away. It's an excellent point.
Because there are different types of geology under the sea cliffs.
Mm-hmm.
And the Hamakua coast up to Honoli'i is one kind of thing, and some other things are almost solid rock, and
Absolutely.
that's a whole different world.
Yeah, so I mean, this type of work and to apply this type of adaptive strategy is definitely like a place-by-place basis. And that's kind of the utility of, you know, using drone technology or having old data sets, because you can focus on one place and inform the changes of that one place. Yeah.
Well, you know, getting to your point, even if you have what is apparently a real solid cliff face right now, if you have, you know, changing weather patterns, you have increased hurricanes and extreme weather events, you could still have undercutting of that cliff.
Not to mention earthquakes.
Yeah.
Absolutely.
Rocks.
So there's so many things to consider. It's
Yeah, at some point it's like a risk assessment of like,
But some of these land masses are much more immovable,
yeah.
relatively speaking. I mean,
absolutely. Yeah, you guys nailing it on the head.
Thank you, Rose. We
Yeah.
appreciate it. It's very engaging.